Thank you for that wonderful introduction. Hi, everyone. I am Ashi, and I'm going to be your guide today as we go into the world of deep learning in JavaScript. So I'm not an expert in machine learning, but my mom is, or I kind of think she is. She designed digital filters for hearing aids, and then later she worked on a speech recognizer at CMU. I spent one summer working in her lab, and I remember it being just a pretty super intimidating experience. People were saying all these words that I did not understand even a little bit, and there were all these very strange mathy sigils written on the walls. And I was typing for someone who was working on a recursive transition network, and we were talking about weights and perplexity and cross entropy. And it was an incredible learning opportunity, but I was also concerned that I could never understand this, or I was convinced that I could never understand any of it. And so learning this stuff has brought me both closer to her, and also I've come to realize that none of that was really as scary as it seemed at the time. In fact, there's sort of a lot of nomenclature and a lot of terminology that obfuscates more than it reveals. And so that's going to be a theme of this talk, that these things, they're not as hard as they seem. So I've been learning this field out of curiosity, with some excitement for the future, because all of this stuff is very exciting, and also with some sense of existential terror, that the robots are coming to steal our jobs and remake our societies and maybe put us in pods like from the Matrix, where you'll have something going down your throat and it'll be sucking all of your blood out. And I have some exciting news on that count, that's pretty unlikely in the near future, because all of these robots are very impressive in one sense. We are doing things that we absolutely could not do 5 years ago. And they're also still extremely stupid in just a fundamental way. So they're probably not going to take your job within the next couple of years, but they are going to change it. And so now is a very exciting time to be getting into this stuff. There's a big wealth of tools and a whole explosion of an ecosystem for machine learning that's growing in JavaScript. And so let's dive in and survey the landscape. My clicker doesn't work. No. There we go. So the landscape we're going to look at is TensorFlow. TensorFlow is, I'll say, the premier machine learning framework. There's a few others that are also very popular, but TensorFlow is the one we're going to look at. And it's available for C++, Python, and JavaScript. The Python bindings link directly to the C++ bindings. They can do almost everything you can do in C++, and so most people just use the Python bindings. So let's compare these two. What TensorFlow lets you do is it lets you describe a graph of computations and send data through it. And so it's able to understand how to process sort of large chunks of data in a performant way. TensorFlow.py can process that data on the CPU, the GPU, or on TPUs. There we go. And these are kind of ascending in the number of compute units, but also descending in the complexity of each compute unit. So GPUs are CPUs with more processors, each of which individually is crappier. That's basically the strategy, because if you're trying to render a lot of pixels to the screen, you want more crappy processors. TPUs are special purpose machine learning hardware that Google developed, which go even further in that direction. They have very low accuracy, or not accuracy, they have relatively low precision, but a whole lot of parallel compute operations, which is exactly what you want from machine learning. So TensorFlow JavaScript is able to process on the GPU, or on the CPU under Node, on the GPU under WebGL, and now there are experimental bindings, TFJS Node GPU, which lets you use the GPU under Node. No word on TPU bindings yet. It's not that important, because the only place you can get access to that hardware is by running on Google's cloud. So in terms of support tooling, there's a pretty extensive machine learning and data science ecosystem on the Python side of the fence. And on the JavaScript side of the fence, it's growing, I'll say, but it's not quite there yet. And there are projects to make it so. So you can get Pandas as a common data processing framework. That's available under JavaScript now. What else is available? There's, of course, TensorFlow. There's Propel is something like a Jupyter notebook, but it's for JavaScript. And so these things are becoming available, but there remains the fundamental problem that if you look up like k-means clustering TensorFlow JavaScript, the first 10 results are in Python, which is, it's sort of what you come to expect after working in this field for a while, because that's just where the community is. I'm sure in like 5 years or so, that'll have begun to have changed. But for right now, the strategy is pretty much going to be to train your models in the sky, like on cloud computing hardware written in Python, but then to run them in the browser using TensorFlow.js. And that is the big power that TensorFlow.js gives us, is the ability to run the same models that have been trained under TensorFlow Python in the browser. And so that's very exciting, because it means that we can create machine learning-driven applications that run entirely on the front end, which means that we can leverage the power of machine learning without data ever leaving the user's device, which is a really big privacy win. We can also train models in TensorFlow.js, and in fact, we can train models partially. So we can take an existing model that's been trained and adapt it to a user's specific needs, again, without the data ever leaving the device or going into sort of a cloud regime. And at this point, you might be wondering, OK, that's great. What exactly, it's called TensorFlow. I'm going to say the word tensor about 500 more times. So what exactly is that? So if you Google tensor on Wikipedia, you'll find this. You'll see, it'll tell you that in mathematics, a tensor is a geometric object that describes linear relations between geometric vectors, scalars, and other tensors. Elementary examples of such relations include the dot product, the cross product, and linear maps. That doesn't really clear it up for me. I don't know about you. I think of a tensor as a big lump of numbers. So you can have a lump of numbers that has zero dimensionality, so basically a number point. We call those scalars because if you multiply them with any other tensor, they will scale it. You can have one-dimensional tensors, sort of these lines of numbers, vectors. You can have rank 2 tensors, which are number rectangles, also known as matrices. You can have rank 3 tensors, which are these like number cubes. And you can have progressively higher ranked tensors, rank 4, 5, 6, 7. They get progressively harder to draw. So TensorFlow is a framework that knows how to do math to these objects, and it knows how to do it in a performant way, which is good because machine learning is all about building models out of these big chunks of numbers. Which raises another good question. What are models? So let's say we have some phenomena in the world. A model is going to be a mathematical description of it. It's going to be the world simplified into math. So to do this, we have to go through a training process. This is where we try and get the system to create a model from a whole bunch of examples. We're trying to get it to infer some deeper truth about the world just by looking at a bunch of examples. So if we take this snake, one way we might train a model is, if we want to simplify the snake into a curve, we might just try drawing a whole bunch of curves, and after each one saying like, oh, does this fit? OK, what about this one? Sort of guess and check. That's going to take a very, very long time, even for a very simple model, because we don't really have any sense of what direction to move in to get better. What we really want is a way to make a guess and then improve upon it to make a better guess until we find a model that's a good fit. And it turns out we can do that. The process is called stochastic gradient descent, which again is not nearly so terrifying as it sounds. So let's say now that we have some phenomena, and that phenomena is the splatter of paint. Let's say I want to model it as a line, which incidentally is not something I would want to do if I care about the splatter of paint as a splatter of paint. Lines don't really retain splatteriness. But lines also have only 2 parameters, which is fabulous because later it means we're going to be able to draw the space of all possible lines in a way that our brains can comprehend. So for now, we're going to render it as a line. And the first thing we need to do in order to do that is to put a coordinate system under it and turn these into XY points. So now I have a bunch of observations, a bunch of data points. And I want to turn it into a line, which basically means I want to perform linear regression on it. You might remember that the equation for a line is y equals mx plus b, m being the slope, b being the y-intercept, which means if we just pick any 2 random values for m and b, we get a line. Now, it may not be a very good line, and in fact, this one isn't. So that point is really far off, and these 2 points are, kind of far off. And if we have to, if we go and perform that offness calculation for every point in our data set, then we get this quantity called loss. So loss represents how badly we're doing. It's like the feeling you get at the end of a relationship. It tells you how off you are compared to the world of data. There's a number of different ways of measuring loss. A very common one is mean squared error. That just means that our loss is going to be taken as the average of the errors, the difference between our model's prediction and the actual data points squared. If we were to write it in JavaScript, it would look a bit like this. So here we've got our mean squared error loss function, which takes some set of data points and a model. The model we're giving it is this higher order line function, which takes 2 model parameters, m and b. These are model parameters because they're the things that we're going to learn during training. They're the free variables that our training process can change. And then for any given line, we go and reduce over all the data points. We ask what the difference is between what the model function predicted and what the data point actually was. We square it, and then we take the mean of all that in order to get the error. So if we do this, then that gives us a fairly good measure of how badly a given line fit the data. And because we have only 2 model parameters, we can visualize this sort of space of all the possible lines and how well they fit the data in only 3 dimensions, which is why I picked a line. So we could put the slope on one axis and the y-intercept on the other. And then for any given point, we can go and ask, OK, how well does this line fit the data? And so we go and figure that out. And then we can kind of go up there and take a look around. We can say, OK, what if I increased the slope? Or what if I decreased it? Would those fit the data better? Or what if I increased the y-intercept? Or what if I decreased that? Would that fit the data better? And then we can take a step in that direction and do it again. What direction do I need to go in order to make the fit even better than this? So here, loss is telling us how to move. It's telling us how to change the model. It's as though we're exploring a landscape, and at every point, we're trying to roll downhill. So the slopiness of a landscape in math is called its gradient. And so this process is called gradient descent. And as you might imagine, there's a lot of tweaks we could make to the process. For example, if we have a lot of data points, computing loss against all of them can be very time-consuming. So we might pick some subset of data points in order to figure out what the gradient is at each step. That would be stochastic gradient descent, particularly if you're the kind of person who says stochastic rather than random. There's also the question of how big the steps we take are, and that's the learning rate. So these are hyperparameters. We feed them to the training process, but they're not discovered by the training process. Whereas model parameters are discovered by the training process, these are tweaked manually, typically until your eyes bleed. So that's it for a line. We know how to now fit a line to some data. But our choice of that function was pretty much arbitrary. We could choose any number of other functions. For example, we might pick an S-shaped or sigmoidal function. And in fact, when I was first looking at machine learning back in my mom's lab all those years ago, this was the most common activation function for multilayer neural networks. It has some nice qualities. It's smooth everywhere, so it's differentiable at every point. And it kind of approximates the firing of a neuron. So at some low level of input, the neuron does not fire. And then as input goes up, there's some point where it does fire. And so for a long time, these were the most popular activation functions for multilayer neurons. And then more recently, a different activation function has become popular. And that's this. This is not a very complicated function. It is a max of 0 and x. And it has a name that it's so like a really overburdened name. It's called a rectified linear unit because it bears a resemblance to the behavior of a rectified linear unit circuit module. And this is now what most multilayer neural networks will use in their activation layers. And it's not as nice mathematically as the S-shaped curve. For example, it has a discontinuity, so you can't, the slope where it transitions from being 0 to being x, that's not defined. Turns out that doesn't matter too much. You can just kind of like not operate in that part of the curve. And apart from that, it has a number of very nice qualities, which is that all of the math on it is really simple. Like, we know the derivative of the straight parts, and it's very cheap to calculate. And all of these things that make it sort of intuitively easy for us as programmers to think about are actually good for the training process because it doesn't require as many operations to do any of the things we have to do during training. And that's important because we're going to stack up a whole lot of these. And so here we can take 2 layers and fill them with these ReLU neurons. We'll make these layers densely interconnected, which means that all of the neurons in one layer will connect to all of the neurons in the next. And so the input to this neuron is going to be a weighted sum of the outputs of all of the units in the previous layer. So each of these units is basically computing a very simple function, that max function from earlier, which means that each of them is kind of an if statement with a configurable threshold, where the threshold is dependent on how it weights all of the previous layers. So a multi-layer stack of neurons is basically doing a whole bunch of nested if statements, going deeper and deeper, creating this great tangle of spaghetti code with all of these hard-coded values that are able to process extremely complicated problems. So the number of parameters adds up pretty fast. This network, which can't do very much, has 16, which means that there's 16 different independently variable things, which means that the model has 16 dimensions. Its loss landscape we would have to visualize in 17 dimensions, which I don't know about you, but I have substantial trouble doing that. These folks have given it a pretty good shot, though. So this is the loss landscape for a image classifier called ResNet, which has about 60 million parameters. And they're obviously doing some pretty heavy projection and whatnot to get it down to 3 dimensions and to make it look even remotely intelligible to our tiny, tiny minds, which, incidentally, our tiny, tiny minds have vastly more parameters even than this. So now we have a sense of what models are and kind of where they can go in the state of the art. The good news is that while it's helpful to know this, you don't have to. There are some pre-built and pre-trained models that you can just npm install. And so let's take a look at those. So the first one I want to look at is called PoseNet. And this is my friend and I. We're at the school I used to teach at. And PoseNet is taking the input from my webcam, and it's going and predicting our poses. It's figuring out where certain key points of our bodies are and then drawing bones between them. And as you can see, it's not very good. It has like the vaguest of ideas where we are, and then the actual bones and key points are jumping around quite a lot. So PoseNet has a bunch of configuration parameters. The output stride pertains to how dense the network itself is. So different output strides will actually load different models. The scale factor is just how much the input image is scaled down before it's fed to the network. And so this is basically the lowest quality setting that I could manage. And I set it that way in order to see how fast it could be. And how fast it could be on my late 2014 MacBook was 8 frames per second. Not the best. If we make it much better, so we can turn up these parameters so that now it's a bit laggy, but our skeletons aren't sort of deforming in some transporter accident kind of way. And the key points are much better attached to our bodies, but we're getting less than 1 frame per second. So on the one hand, it's pretty cool that you can do this in the browser completely client-side. But on the other hand, if you were hoping to implement Beat Saber with it, I would drop that dream right now. It's not happening anytime soon. So I struggled for a little while to think of something really genuinely useful that we could do with this, a slow way to approximate the positions of body parts. And I did actually come up with something that is a problem that perhaps you yourselves have experienced. So I've got all these photos, and I want them to be in a grid that is responsive to the page. But of course, when I resize the grid, the faces don't stay in frame. Like, we have lost that cool old lady entirely. And while I think the tree is nice and all, we're really losing something important about a lot of these photos by the fact that the faces are not correctly identified. And so, of course, we could manually position set the background position based on where we know the faces to be. But that only works if I know the images in advance. If they're provided by the user, we can't really realistically do it. So let's look at how we can use PoseNet to solve this problem. And first, let's look at how you use PoseNet from JavaScript. So first, you need to npm install it. I've sort of skipped over that part. Next, you want to import it from TensorFlow models PoseNet. So TensorFlow models is a namespace that has a whole bunch of models that the Google folks have released with nice JavaScript APIs. So here you're not using the model and the TensorFlow methods directly, but you actually get sort of a friendlier interface to it. So the first thing we need to do is load the model. That's asynchronous because it's going to pull the model in probably from Google storage. And then our estimate pose function takes an image, and that'll just be an HTML image. So what we want to do is PoseNet needs a square image of some configurable size, but generally 256 by 256. And so we are just going to reshape the image that we get to be that size, possibly distorting it in the process. Then we're going to await this estimate single pose function. PoseNet also has an estimate multiple poses function, I believe it's called. And you call one or the other depending on whether you think there are likely to be multiple people in the scene. The pose we get back is a bunch of key points. So it'll be like nose and then a coordinate, left shoulder and then a coordinate. Sorry, I guess that's an object containing a bunch of key points, because then I push onto them there. So we're going to add a few more key points. The box points are just going to be northeast, northwest, center, and so on, so we can see sort of where PoseNet thinks the borders of the image are. And then we return the whole thing. So if we plot those points on with just a single photo, here's what we get. So these are the box points that I mentioned earlier. There's the center of the box, there's the east of the box, and so on. And then we've got PoseNet's key points, which you can sort of see clustered around her face. So here's her right ear. That's maybe kind of true. Her right eye is pretty much in the right place. Left eye looking good. That's not a shoulder. That's her right hip is not at her. OK, so some of these are really wrong. But one thing that tends to be pretty correct is her nose. And I looked at a bunch of these photos. Noses tend to be pretty well detected. Noses are also the very center of a face, which is perfect. And so if I select that key point, I can keep her in frame no matter the size of the image. And of course, there's a little bit more code supporting all that. So let's take a look at that. So this is done in React because it is actually illegal for a JavaScript talk not to mention React. And it's using RxJS because every time I think I have a use case for RxJS, it turns out I don't. It's just like not that useful. But for this one, I used RxJS, and I was like, this is actually working out pretty well. So this is the one useful case I found for it. There's someone who's going to really hate me for saying that. So anytime you see any of these functions that end with $, or the variables that end with $, they're consuming a whole stream of values. So we're going to get streams for the size of PoseNet that we want, which will just be 256 by 256, and also the image's source. We're going to watch the size of the frame that we've been asked to draw into. That's happening with get-bounding client rect right now. Probably not the fastest. Probably should use a resize observer. And then we load the image and then call that estimate pose function on a stream. Estimate pose is just the same function that we saw earlier. We figure out what size would cover the frame. So we figure out basically how much we need to scale down or up the image. We go and reduce all of the key points that we get from PoseNet, which are actually they're put into an array. We turn those into an object keyed by the name of the point, which then lets us look up the key point that we've chosen to center. So in this case, we'll be looking up the nose. In the RxCist part of this, we start centered on the very center of the image, which is usually pretty good. And then once the pose has loaded, we find the position of the part that we want. So we find the position of the nose, and we switch to centering that. And then finally, we figure out how much to offset the content, and we return the whole stream of states. And so if we use this module on our gallery of people, you'll see it takes a second for the poses to load. You can tell it's loaded once all the key points get drawn in. And then once they're loaded, we can resize the entire gallery, and everyone's face pretty much stays in frame. It's kind of lost it's keeping, in the photos with 2, it's sort of picked one person. Ideally, we would probably try and estimate multiple poses and then keep sort of the centroid of all of their noses within frame. It's probably also the case that if we have access to these beforehand, we'll want to do this offline somehow. So you could make it part of your build process, or when someone uploads an image, you could go and perform the pose detection then. It's probably not ideal to be doing this on every single person's computer, if only because the model is rather big and loading it every time takes quite a while. But it's still, for a relatively small amount of code, we've solved a problem that I at least have run into quite frequently, and so I was quite pleased about that as a practical application for machine learning. So now let's apply it to something just much less useful. now we're going to do some transfer learning. Transfer learning is when you take an existing model, you sort of cut off the end where it actually figures out how to output an answer, and you train a different model that can output a different answer using a lot of the using the internal representation of the previous model as input. And the problems that we're going to be training for is this. Namely, we're going to try and I'm going to use Tallulah, my elephant friend, as a controller for Pac-Man. This is actually an example within the TensorFlow GitHub, so you can go and look at it there. So the way it works is we add examples for each of the different control directions. So I'm just flipping Tallulah around. I'm trying to get a variety of different ways that I might hold her as examples. And then you click Train Model. We see the loss goes down. We even have a sense of what that means. And then we hit play. And so when I'm playing the game, you can see that it highlights what it thinks that I'm doing. And it works actually pretty surprisingly well. I'm able to control Pac-Man. I think I'm going to be able to go and eat that thing. And then I start to get frustrated because it's difficult to control Pac-Man with an elephant. I'm holding Tallulah differently, I'm noticing. And this is not looking good for me. Yep, I've been eaten. And thank you. It's very challenging. Nothing destroys a friendship like using your friend as a game controller. We're still friends. So let's take a look at how this works. So here we're going to use the models a little bit more directly in this example. So we're going to actually pull in TensorFlow.js, and we're going to use this controller dataset utility class in order to store all of the examples for the different classes. And so every time I click the button to add an example, the controller dataset is basically going to take a tensor and add another slice to it, which is the current image from the webcam. So first, we're going to load the existing mobilenet model. This has a model description file stored in Google Storage, which then points to other resources stored in Google Storage. So we call load model on that. And then we go and suck out an internal layer of that model. So we're getting this conv pw13 relu layer. And we'll look at what that means more in a second. And we take that layer, and then we construct a new model that takes mobilenet's input and has a lot of mobilenet's guts, but it ends before mobilenet's output. So it ends at this layer that we've gone and pulled out of the middle. And so what any image classifier does is it starts from an image. So its input is, I think in this case, 256 by 256 pixels. And its output is going to be probability classes. So the output will be like the probability that the image contains a cat, the probability that the image contains a dog, banana, toaster, whatever. And those, so what the network is really doing is it's kind of reshaping from pixels to probability classes. And what we've done is we've cut off the bottom. So we've kept most of the reshaping, but we're like, OK, we're going to output a different set of probability classes. And so we're going to not perform some of the last steps. And instead, we're going to learn how to do some different last steps now. So then every time I click Add Example, this happens. We grab a frame from the webcam, and then we add it to the controller data set. Notice that we are predicting, we're running it through that sort of mobilenet pseudo, the detached chunk of mobilenet that we created before. So these are the examples that our model is going to train on. And the input to our model, the end bit, is the output from that inner chunk of mobilenet. And then the output of our model is the training label. It'll be up, down, left, or right. So then we describe our model, which is just going to be a sequential model, which means it's a stack of layers. The first layer is going to take it's going to take the output of mobilenet and flatten it, so it's just about 12,000 neurons in a row. And then we're going to have a dense layer with ReLU activation, ReLU being the activation function we saw before. And there's a configurable number of units in this layer. You can see how the network behaves with more or fewer. The default is 100. And after this densely connected layer, we have another densely connected layer with a different activation function. So, and the activation function is softmax, which is, I don't know why it's called softmax, but what softmax lets you do is it lets you produce a probability distribution, which is what we want, because I'm either holding Tallulah up, left, right, or down, and the probabilities of any of those should sum to 1, and softmax gives us that behavior. So then we set up an optimizer to train this model. The optimizer we're using is not classical stochastic gradient descent. It's ADAM. ADAM is a stochastic gradient descent technique, but it's a little bit smarter. Specifically, it's a little bit smarter about the size of steps that it takes. So it's able to dynamically adjust the learning rate in order to produce a more optimal model and train a bit faster. We compile the model, which turns it into a representation that TensorFlow is able to execute. And then, and we compile it using a certain loss function. So we have to say, like, hey, when you're training, here's how you should figure out the loss for a given example. The loss that we're using is called categorical cross entropy, one of the many confusing words that I didn't understand when my mom said it. But now I kind of do. So the question here is, we have, as our last layer, a softmax layer, which means that we are trying to get a probability distribution out. So the question is, how far off is a predicted probability distribution? So one of our examples will be something like this. It'll be a photo of me holding Tallulah upside down. And the correct answer will be 100% chance that I'm holding her down. If the prediction is this, it's like 40% chance that you're holding her down, 50% chance that you're holding her to the left. How off is that? It's like, it's off by some amount, clearly. It's like not right. Would it be more not right? Like, how much worse is it that it's actually guessing the wrong class? And how bad is it that the probabilities are all kind of smeared out more than they should be? And so categorical cross entropy gives us basically how much a model will confuse different probability classes. And it gives us that quantity in a way that lets us train a neural network. So it's sort of a well-behaved measure of how badly we're doing when our output is probability classes. All right, so then we compute a batch size. The batch size, again, is how many examples we're going to randomly take from the size of all examples in order to compute loss at each step. And then we train. So when we train, we call this model fit function. That actually starts dispatching actions to the GPU, and the model begins to train. And we get a callback after each training epoch that lets us update the UI with the current loss, and also not block the browser thread entirely, because we can do this await next frame, which basically just does a request animation frame and waits for it in a premise. So then when we play the game, we just run the input, whatever the current input of the webcam is, through each of these layers. So first, we have mobilenet, or at least the first part of mobilenet, figure out a prediction for the image, for the actual input image. So here we've run it through all of the layers except the last few. And then we take that activation and we run it through our model, the one we trained on our examples, to figure out the predictions. And then we do this argmax thing, where we just figure out what prediction had the highest probability. And so if that is the output of our model, then taking argmax of it will say that, OK, element index 2 had the highest probability, and we map that elsewhere to be down, and then we send the down event to the game, and we're playing Pac-Man with an elephant. So that's basically it. But let's take a look at something we sort of glossed over earlier, which is this kind of funny-looking internal layer with an odd name. To get a better sense of what all this was about, I decided to go and load up that JSON file and just kind of poke around. So I'm doing this in the dev console. I went and fetched the model, and we can see that it's a Keras model. So Keras is now actually a part of TensorFlow. It's a library that lets you describe models as a series of layers and sort of makes the process of describing a machine learning model a bit easier. And so we can see that this model has 88 layers, and that's a whole bunch of layers. So we have an input layer at as the first one. That kind of makes sense. And then we kind of have this repeating cycle. We have a convolutional layer, and then a normalization layer, and then an activation layer. So the normalization layer just kind of ensures that our values don't get too far outside the range of 0 to 1. The activation layers are the ReLU layers that we saw from earlier. They're sort of doing some sort of arbitrary processing. Convolutional layers sound sort of a bit scary, but aren't so much. They're basically Photoshop filters. So a convolutional layer takes a bunch of pixels, and specifically it takes a chunk, and it takes each chunk of a certain size and runs it through a filter in order to produce another output pixel. And so the filter is just a bunch of numbers. There's one number in each of those cells. And to get the value for the output pixel, we're going to multiply the corresponding cell of the filter with the corresponding cell of the input, and then we're going to sum all of those values. And then we walk the filter across the image in order to produce all the output pixels. So the key thing about using convolutions in machine learning is that this filter is trainable. So you can, it has a certain size. That size is 3 by 3. You can configure the size as one of the tuning parameters. The fact that it's trainable and the same across the whole image, it means that the system learns progressively higher level features as you go deeper. So these are basically Photoshop filters. A lot of Photoshop filters work this way. But when you stack them up and then give them a certain goal, let's actually just look at what happens when we do that. So here I've written a little something to decompose mobilenet and show all of its internal layers. And so we can kind of see that the first convolutional layer is sort of doing something like foreground extraction. Progressively deeper layers are starting to do, like in the third layer, we see edge detection. In the fourth layer, we see sort of different kinds of edge detection. It starts to get a little bit challenging to articulate what these layers are doing because we haven't actually given them a goal, except for the end goal of classifying different photos of different things in different ways. And that's the other behavior you see. We're going from images that are the size of the input down to basically like single blobs of pixels, which is the reshape operation that an image classifier must do. We have to go from images to ultimately, like, is there a dog in this photo, which is just a single number. And it's doing it by basically applying a whole bunch of crappy Photoshop filters to the image, a task that if someone said you want it, you would be like, no, absolutely not. I'm not going to tell you like what 20 Photoshop like filters will, if applied to an image, tell you if there's a dog in it. But that's the beauty and also the kind of like crappy secret of machine learning. It's a big pile of simple operations that you yourself did not have to tweak. It's a bunch of nested if statements that you didn't have to write. And I hope seeing that makes it all seem a little bit less scary. Because the world does seem a little scary these days. We have a huge amount of information to process, and our interaction with all of it is increasingly heavily mediated by machine learning systems, by other people. And none of these systems, not the people or the machine learning systems, are perfect. They've just been trained on whatever data we've given them. And just like us, they can internalize the biases of that data. And just like us, they can be put into the service of whoever wants to wield them. So there's a proof that neural networks are universal approximators. That means that for any computable function that you can imagine, you can come up with a neural network that computes that to any level of accuracy. Although whether we have the techniques or data to actually train such a network is sort of a different question. Still, I think we're getting there. I think that if you believe, as I do, that cognition is a computable function, we're moving into a world in which the fundamental tasks of cognition are amenable to, are accessible to neural networks. They are now things that we can train machines to do. So these, as you probably figured out, are not real faces. These were generated by a generative adversarial network, which is a kind of network that uses another network to compute its loss function. The two networks sort of train each other. They improve upon each other, learning to dream up things that look like celebrities. And this is not Obama. This is a machine learning generated Obama, synced to a recording of an actual Obama speech. And of course, there are systems that can generate speech that sounds like anyone as well. So how do we deal with this? With a world where we can't really trust our own eyes and ears? One way, I think, is to ignore it and just say, these technologies aren't that good, and I don't think they'll become that good. I would say that they're not that good yet. But if cognition is a computable function, then our societies and ourselves are games. And these robots are very good at playing games. But I wouldn't despair. In the history of computation, we see these tides. So first, all of the important work happened on big mainframes. And then processors became better and smaller, and all work sort of moved to personal computers. And then networks improved, and we put everything in the cloud. And so now we're beginning to see the tide go out again, as we begin to realize how much power we've given away, how much power there is in knowing everything about everything about everyone, and how much danger there is in relying on centralized systems outside of our control to feed us with knowledge. But I think that these technologies don't have to be opaque. They don't have to be centralized. We are able now to perform these tasks on people's machines, on people's phones. We can hold the power of robot minds in our pockets, and we can use them not just to create forgeries, but to detect truth. So everything we've seen today is just the beginning. It's sometimes janky and sometimes quite impressive, and it's all quite promising. But I think in a few years, it's going to look downright embarrassing when you can have a full conversation with your AI assistant, and the memory of your voice will never leave your wrist. Thank you. If you're interested in this, these are some good people to follow: Paige Bailey, Francois Chalette, Ian Goodfellow. I'm Ashi. Thanks.
Ashi, we invite you to have interview. By we, I mean me and Coco.
Oh.
So, yeah. And first of all, thanks for your talk. It was awesome. Now, the first question is, do you think that JavaScript has place in machine learning? So you show a couple examples and show clearly that performance is not that amazing right now.
Yeah.
And so, do you think JavaScript will have future in machine learning, or is it the best that we can get right?
Definitely, and I think I think it's, like performance is only getting better, right? The reason that the performance is not as good under WebGL is because it's WebGL, right? There's a lot of protections in there to let us access graphics hardware on, like through the browser from sort of untrusted code. That's going to get more performant. The Node version, I have not done benchmarks, I haven't seen benchmarks, but there's no reason the Node version can't be just as performant as the Python version, or possibly more so, I don't know.
Okay, so one question. Do you think that people who doesn't have a computer science degree, should they even try to use TensorFlow, or you should have some sort of education first before trying to do anything in machine learning?
I think there's no harm in trying, right? The examples are pretty accessible. You will encounter some terminology that just feels intimidating, but it's not, none of it is really that hard. Like, none of the concepts are really that challenging. In some cases, like some academic papers have, like, here's a proof that Earth mover's distance is valid for like this particular operation. You might not understand that, but you also rarely have to understand that in order to implement those techniques. And so yeah, I think it's more accessible than it appears. And we're seeing sort of more and more accessible ways to learn about it. Like Google actually recently released a machine learning crash course that's like 15 hours of videos, which I went through as part of preparing for this talk, which I would highly recommend because it makes a lot of these concepts that have been sort of shrouded in inaccessible math a lot more accessible. Yeah.
The last question I want to ask is, what do you think about transfer learning? So, for example, when you take a already created model that other people created, trained, do you think it's the best way for approaching machine learning? So you better find some ready to work model and then use it, or it's better to train it yourself, like create this model from scratch by yourself in JavaScript or in the browser?
I think transfer learning is probably a better way to get started if you have a model that already does a lot of what you want to do. Because training an image classifier is just, it's either going to take an extremely long time on your laptop, or it's going to be a little bit pricey to train in the cloud. Maybe not that pricey, like you could probably train it for like $15, $20 worth of cloud compute, but you might have to do that several times. And an existing image classifier has already been trained, that work's already been done, and most likely you will be able to reuse a lot of that, because most of the work we saw is like extract foreground from background, find images, find like faces, find things that look like common objects. So if you're doing something completely different than any existing model, it might make sense to train from scratch. But I think especially if you're just getting into it, transfer learning represents a way to do that very accessibly. Like you saw how fast the transfer learning took.
That's awesome. Thank you a lot.
Thank you so much.